This is video help for problem 23.2. Problem 23.1 and 23.5 are reasonably, helped, assisted by our written homework advice. I really don't need to add anything there, but I do need to talk to you about 23.2 because we have no homework advice for that posted as I see. Now, here's what we're going to do. We've calculated a phase. We've got a formula for a phase involving, the velocity of the fluid of blood in a vessel. And if you have a reasonably more accurate than plug flow model, you would need to ask that the velocity vanish at the wall. Laminar flow does that. That's a boundary condition. At the wall, the blood flow has to be zero, and then maximum in the middle. Thus, the maximal variation is at the wall. The derivative, I've got a little quadratic model here. The derivative is biggest at the wall. So let's look at a voxel next to the wall between, a minus delta y to a. And the change of the variation of the velocity then over that voxel, I just take a minus delta y squared, at 0 at y equal a. And I just write this out, write this into, I factor this out so that I can compare the delta y squared to the delta y. And if this is small, then it's just linear in delta y. And that's what we were assuming, and that's how we derived a formula. So I asked that this be much smaller than 1. And as a rule of thumb, if I say then, something much less than 1, what I'm saying is that my error will be characterized by epsilon, and if I want a 10% error, let's say epsilon is less than 1/10. That satisfies this to 10%. Well, if delta y of our voxel is small enough, then the phase will be linear in delta y here. In part B, you don't need delta t and L, you'll need them in C. And in part B, you can just do it in a half a line. Check yourself. Check your answer in part A, from part A. In part C, alpha is defined by the coefficient of y minus y0 when you expand the velocity, velocity profile, velocity function of y. If I expand it around y0, so I'm expanding in y minus y0 and then call that delta y because we're interested in this variation over a voxel. And the higher order terms, if delta y is small enough, we can ignore them. And as a matter of fact, if it's satisfies what you got in part A, it's certainly going to satisfy it everywhere else. It's actually when y goes to 0 in the center of your vessel flow, well, then it's just a constant. So, like before, I'll divide out the Vx max. Vxy then is 1 minus y0 plus delta y squared. I'll define that as delta y. I expand it out, and I now have got myself a coefficient that I can define, that I have defined in terms of alpha. So now I know what alpha is for this problem. And now if I know alpha for this problem, then I can calculate the phase for this problem. By the way, there should be a minus sign, 23.17. So when I take that formula with a minus sign, I get a plus. I know that guy. I'm going to be at the edge, so y0 is a. I know this. And by the way, when you're done, when you're relating g, through what, gamma bar, delta k and stuff, then you'll get gamma bar, and so remember gamma bar is gamma over 2 pi, you're going to get a 2 pi, and tau, the echo time, is half of nx delta t, nx is lx over delta x, and delta x is y, delta y, and you can figure out everything. The signal loss is defined to be that function f of alpha in 2318. And then you can use table 23.1. If you keep this thing there's a factor of pi that's going to come out when you're done. And if you keep that pi, don't put a number for it, and you'll get a number times pi, and you'll immediately be able to compare to table 23.1. You'll get an answer, and you can actually check your answer when you take the number you got out of phi, if you do put in the pi, and check the 1 minus sinc phi, which came into the signal loss formula, check the table. So I hope that helps.